Yeah. The noise is tough. We're going to get started. My name is Bob Brennan. I work for Integrated Manufacturing Systems, and we're based in the U.S. We do wireless barcoding and data collection systems from factories, so people that are managing their inventory control and a warehouse distribution, that sort of thing. So we specialize in mobile applications and wireless access to those, so that we push the data collection piece down to people on the floor who are the first to learn about a transaction or be able to process it, right, for the betterment of the whole staff. So what we're going to talk about today is kind of the wireless component to that, and talk about the convergence of Wi-Fi standards and cellular standards, how they're merging into a kind of a single set of challenges, and then some of the development considerations around that. Okay, some of this is probably going to be a little bit deep, but it's meant to try and tie together the miracle that is wireless. My foundational statement: it's a miracle it works, okay? And that it's kept pace with the adoption of these technologies to continue to move faster and faster with more and more people, okay? So, that being said, some level setting, basic physics on what's going on. We'll talk about Wi-Fi, we'll talk about cellular, we'll talk about the convergence between those. And part of that convergence is the development aspect of things, and then some Q&A if we have time. So going back to your grade school, right? A wave is promulgated off of an antenna, right? So the center line or the reference line of an antenna is the center point, and we have a concept of wavelength. How many times does it take to do a single cycle? How high is the wave, and how many of them do we get in a second, okay? With every wave, electromagnetic wave, we have the mechanical wave that's going off, and perpendicular to that, we have a magnetic field, right? And there's nothing we can do about it. It is always at a 90-degree angle, and the energy is going one way, and the magnetism is going another way, okay? And they propagate at the speed of light. So we can't go faster, we can't go slower. So just to cut away on a standard rubber duck antenna that you're likely to see in one of your access points, right? That's at the top. The bottom is the whole covers off of it. And if you look real carefully, you'll see the white part on the bottom, and then there's a metal clip. It's a dipole antenna, and all that means is that there's two pieces, two elements to the antenna. So if we go back to that drawing, right, the center line of that drawing is some of the wave is going to hit the outer edge of the antenna, and some of it's going to hit the inner edge of the antenna, or when it broadcasts, it's going to do the same thing. So there's a graphic of how things work, okay? So as the electrical energy is hitting the antenna, we're causing a shift back and forth, right, in the energy. So we talk about things running at gigahertz speeds, right? And this is one of the miracles to me. Gigahertz means billions of fully formed waves per second, okay? That's an awful lot, right? That's an awful lot of bandwidth. And you would think that that should be sufficient for everything we want to do, and it's not. So an antenna, a particular antenna builds out a particular profile of radiation, right? There are people who work their entire lives building antennas to get the profile that they want. But in general, one of those little rubber duck antennas is called an omnidirectional antenna. It creates this donut of coverage, okay? And the coverage goes perpendicular to the orientation of the antenna. So the orientation of your antenna plays a huge role in how successful your Wi-Fi is, or any network is, your television, your Wi-Fi, your cell phone, your baby monitor, kind of everything that runs in the radio spectrum, okay? Sure.
Radiation pattern.
Yep.
No. How big is this
So that depends on what we're pushing through the antenna. And we're going to get into that. Okay, it's cool. So polarity is the concept of the orientation of the antenna and where the energy is going. Right? In the perfect world, wherever that antenna is, whatever is doing the receiving on the other end, those antennas ought to be aligned. And when they're not aligned, we waste a lot of cycles trying to communicate the same sort of thing. Okay? So in an omnidirectional antenna, and I'm just showing you, there are two different antenna designs, right? So one's a big fat round donut of a thing, and the other one has more, is squished out and provides a pattern that's going to reach farther, but not reach farther up and down, okay? One interesting thing you'll note is that in the center of both of those, in the center of every omnidirectional antenna, the dead spot under the, right under the antenna, there's no coverage. And I can't tell you the number of times that we go off into a factory, we do a layout, we put a bunch of access points out. We get the IT guy out there because they always want to back check, and they have their iPad or their phone or their whatever, and they're checking their RSI on us, and they stand right under the thing. It's like, man, this is terrible coverage. It's like, do me a favor. I don't care which direction you go, 3 steps to the left, right? And it works. So, if we take any regulated antenna signal, okay, so we're talking generic right now, but just think in terms of Wi-Fi. The energy that comes out of a Wi-Fi antenna is limited. Every country has kind of a cap on the amount of energy they can put out. So one way to help with this is we add gain to an antenna, and all that gain is, that's a miner's hat, right? And the thought here is that if I was in a coal mine and I lit a candle, right, you get kind of a dull light across a whole bunch of it. But if I light that candle and I put the reflector on it, now I'm taking all the energy from the candle and I'm putting it someplace, right? So I get a lot more energy focused on a narrower beam for a much farther distance than I do in an omnidirectional sense. Does that make sense? All right. So a directional antenna has the feature of being really narrow, but we take that same amount of energy, right? So in Physics 101, if we add gain to an antenna, we take the signal strength and we extend it out much farther than we would with an omnidirectional antenna. And when the 2.4 gigahertz radios came out, years and years ago, the wavelength on a 2.4 gigahertz signal is roughly the size of a Pringles can. So what people would do is they'd take an antenna, poke it through the bottom of it, and they'd have a ridiculously tight antenna pattern that you could take 2 Wi-Fi things and put them about 2 miles apart, right? And be able to communicate with one another. It's kind of cool, right? So this is a view of omnidirectional versus a directional antenna. One of the problems that you run into, and we're going to talk about it in a couple of slides, but one of the problems you run into is these are shared, all of the Wi-Fi, whether it's Wi-Fi, whether it's cellular, and those are the kind of the 2 things we're talking about, right? They are bandwidths that nobody is guaranteed access to, okay? You just need to be yelling at the right period of time when there's freedom for you to get your shot. There's no scheduling, there's no task list, there's no queue of you were first and you're next. It's like kindergarten, right? Whoever yells the loudest gets the attention. So what that means is some of the interference that comes into any wireless network is other people who can communicate with the access point or with the antenna or the cellular thing. They cause interference to you and you do to them, okay? because everybody can be heard. And the analogy I use when we talk about putting networks in, it's like a cocktail party, right? If the few of us were hanging around right now, we could talk in normal voices, right? If you were at the party last night, right, there's 300 people in a room, and there's just noise in the background, we need to start yelling at one another, therefore the raspy throat, sorry, to be able to have the same communication, right? And how many times last night did somebody have to lean in and say, I'm sorry, try that again, right? So retries, collisions, right? Real simple concepts. So what are some of the things that cause problems, right? We have a transmitter, we have a receiver, and when we send off a signal, even if it is directional, it's going all over the place. It may only be in a 20-degree arc from where we're starting, but it's hitting things, it's getting absorbed by things, it's bouncing off of things, okay? So signals are arriving because you can think of it as a curve when it comes out of the antenna, and as it goes and careens off of things, it gets wobbled in all sorts of shapes. When it lands at the receiver, it can show up at the antenna on the receiver at different times, okay? All the while, the energy's going back and forth. So the receiver and the transmitter have to agree on how do we put Humpty Dumpty back together again, because the signal that's arriving is sort of broken, right? It's interfered with. Interference only happens at an antenna. So the idea that there are millions and millions of electric waves coming through this room at any given time doesn't matter unless it's hitting an antenna and we're trying to discern what it is, right? And that's a hard concept to get your head around, because most people think of it as discrete things you learned in physics class, and they did the ripple tables, and you saw waves in the water and where they intersected and so forth. The only interference that matters is when somebody's listening for it at the point of an antenna, okay? So you have things that are in phase where two waves are additive, or you have them 180 degrees out of phase where they completely wipe each other out, or you have different waves combining with one another to create some anomaly of a wave, right? So when I said earlier, it's a miracle that anything actually works, this is a good part of it. So when it happens when we don't expect it, it's called interference. Smart people decided that, hey, we can create our own interference and have a property come out of that that's actually really beneficial to us, right? And the concept is called beam forming. And what it means is we have some number of antenna, an antenna array, or just sometimes it's just two. And if you look at, I was joking around the ripple table. I pulled up a tool to create ripples, and right now they're in sync. So both antennas are sending out the same signal at the exact same time. And you can see the pattern of interference, right? So the places where you see the little arcs, those are where the energy between the two things have expanded, right? They are completely in phase with one another. And where you see the lines, those are where everything's canceling out. You can imagine that instead of me hitting both things at the same time, if I start out of phase, those lines are going to shift, okay? When those lines shift, in radio world, it's called beam forming. And beam forming is one of the foundational new techniques that's used in both Wi-Fi and cellular, okay? And that all of that's happening at the scale of billions of cycles in a second with all of the junk that can happen, it is a miracle. And kind of the same thing, right? So we send off a perfect wave by the time it gets to the other side, and I think I kind of buried the lead of foreshadowing. The concept is, if it happens and it's not intentional, it's a problem, potentially, but we can also flip that around and make it a benefit. Attenuation is the process where a signal gets absorbed or slowed or deleted completely. And just this was helpful. If you have Wi-Fi at your house, right, where does the signal go? How does the signal propagate? Where do I get good response? Where do I get bad response? Just some of the materials. Wi-Fi signal will go through a glass window without any problem. If you have a brick wall, you have some problems. If the brick wall has metal in it, you have even more problems, right? So understanding the environment where something's getting laid out is critical to being able to design and deliver a network that's functional and usable for people, okay? Now, it is, in a design perspective, it is better to have less capacity than you need and work up to the edge than it is to have more capacity than you need, because when you have more capacity, all of the access points and all of the devices just sit and argue amongst one another and interfere with one another, okay? So we did an installation where somebody else put the network in, and it was a fairly small manufacturing environment. And kind of at every other cross member, they had an access point, right? And these guys were very proud of their network. And I took our analyzer out and I was like, it's nothing but noise. Like, we're gonna have a problem. And so I had to pull the team together that was from the third party. And they said, what do you think? I said, I think if you shut every other one off, like, I'm not gonna break the news to the customer that you oversold this. But if you don't, I'm going to have to say something around, you have too many of these things. Whoa, so too much is worse than too little, because we can fix too little incrementally, right? So, what about mirrors? Yeah, so anything that has metal in it, right? A mirror by definition would have, doesn't matter, right? Doesn't matter. It's the density of that material, right? So silver, lead, it's bad, right? And so we end up playing that game, right? The things that help move signals around, metals, things where the signals bounce around, right? So we have the multipath thing to have to deal with. Anything that was ever alive, anything that's cellular based, you and me, right? Cardboard, paperboard, packaging, anything that ever was alive that's cellular, okay, is a sponge for networking, wireless networking traffic, okay? You want to have some fun, take a cardboard box, spritz it with water, put it over your access point, and nothing will work, okay? So our job is in a warehouse. It's nothing but metal and cardboard, right? Packages of product. Who knows what's in the package? But I can tell you right now that if we have stacks and stacks and stacks of paperboard and it gets humid, problems chase humidity. The more humid it is, the worse the problem becomes, okay? So we're gonna try, we have a fixed amount of bandwidth, whether it's cellular or it's wireless, right? So the trick is to get as many requests onto the network and process and get you off the network as fast as possible, right? Because the medium is shared and no one's guaranteed access to coverage, right? So that concept of how do you get people on and off, right? All of the techniques that you're gonna see as we talk through kind of what have been the improvements and what are the big things, the big ticket items right now, everything is around answering the telecom request, processing it quickly, and getting on to the next one as fast as possible. So the idea that if you think about this in terms of progress, right, and in terms of app servers, for instance, right, the concept of being, and I always get these screwed up, which is state aware, whatever, the one that doesn't remember anything about your last transaction, right? That's the one you want to be here, right? Get in, get out, let somebody else go. If you maintain context in any sort of way, you are slowing down everybody, okay? I'm sure somebody will. So let's get into the Wi-Fi business here. I don't want to spend a whole lot of time on it, but back in 1999, we had 802.11b. You move forward. So does anybody in here in a corporate environment have Wi-Fi 6 enabled, which is AX? Anybody have AC? Yeah, good. Okay. Wi-Fi 7 shipped this year. Vendors have started shipping equipment against it this year. It's a race to who's first. The cool thing is there aren't any clients with Wi-Fi 7 devices yet. So you've got access points that won't work, or they will work because they're always backward compatible, right? But the idea that we were first to market, it's like, that's cool. Nobody can use it until the rest of the vendors catch up. A couple of things to point out in all of this, right? One is when we first started, we had one frequency. It was 2.4 gigahertz. Okay. As we got into 802.11n, that was a big change. We started using 2 and 5 gigahertz at a time. Okay. And you'll see the maximum throughput jumped tenfold. It went from 54 megabits a second to 540 megabits per second, right? Everything that we're talking about is bit-wise, okay? So the 2.4 billion bits per second, or waves per second, there's a whole lot of headroom in there. If all I'm trying to move is 540 and I have 2.4 billion, you can start to see the scale of the inefficiency of all of these things when that's the best we can do. Okay. As we move forward, you'll see that we get to gigabits per second, up to 30 gigabits per second for the new stuff. Some of the techniques that they use to do that are these modulation schemes, and I will talk more about that concept in a few minutes. The other thing are streams. So streams are just individual radios. So your access point is not just one radio if you're at 802.11n. Right? It's up to 4 radios if it's implemented completely. And 8 radios moving forward, and 16 radios in the current one. And they start having this concept of being able to band this stuff together. Okay. The modulation scheme is really, it's interesting if you have a math background at all, and we're going to touch on it in a second. So in 2.4 gigahertz, depending on where you are in the world, there are certain bands or frequencies that are licensed to be able to be used. It's a range, they're 22 megahertz in width. There are 11 channels allowed by the FCC in the US. Europe has, for most of Europe, it's 13. A couple of countries in Asia is 14. The problem with that is we have these channels, but only 3 of them at a time can be used because all of the other ones overshadow the channel that's there, and you get something called co-channel interference. So in 2.4 gigahertz, we have 3 channels, okay? Keep that in mind as we walk through the next couple of slides. And the channel is really, it's a 22 megahertz wide branch of frequencies, right? So yeah, we have 14, but you can only use 3. So this is something that if adjacent channel interference just means that I have my Wi-Fi set up to use channel 1, 6, and 11. Those are the 3 that we can use, and there's no interference between them. And my buddy Gary comes in at to my network with his hotspot running on his phone. It has nothing to do with my network. And he's, for whatever reason, the phone company says, we're going to use channel 3. Well, what's happening is any traffic that he has is creating interference on 2 of my 3 channels. And he has no idea about it, and I have no idea about it. Right? We have no control over that. Co-channel interference is when 2 devices are talking, 2 network devices are talking on the same channel to mostly to different access points. Or you have 2 access points that are running on the same channel and they're too close together and they can be seen by one another. Okay? Both of those cause a huge amount of problem. In 2.4 gigahertz, one of the other problems you run into is it's Wi-Fi, it's Bluetooth, it's Zigbee, microwave ovens, because 2.4 gigahertz is the frequency that water molecules, when they get excited, vibrate and your food warms up. That's how a microwave works. Cordless phones, baby monitors, wireless video projectors, all kinds of stuff runs in 2.4. It's a disaster of a space to get anything done. Okay. Jumping ahead to Wi-Fi 7, there are 59 individual channels, okay? In 5 gigahertz and 6 gigahertz, none of the channels bump into one another, so they fix that problem, right? So just think about it in this terms. The more channels we have, right? They're like lanes on a highway, right? We got a 3-lane country road sort of thing versus a 56-channel super highway. All right. We'll talk about the rest of this in a minute too. So, because we're talking about Wi-Fi access points, they're the bridge between the wired and the wireless environment, right? They're single-threaded, they're half-duplex. What's that mean? It means that a device, an access point, can talk to one and only one client at a time, right? It's like a walkie-talkie. It's either listening or it's sending, okay? And that has been a huge limiting factor for a long time, right? So if we were talking about 2.4 million cycles, well, half of those are coming in and half of those are going out if we have kind of a relatively balanced network. So our effective throughput drops in half, okay? Kind of like an old switch, or a hub in a network. I just kind of plug it in and it broadcasts to everybody, right? As we move further up with Wi-Fi 6 and beyond, that limitation is gone because there's enough radios in it where we've got full duplex going on. And the math that it takes to have that work, it makes my head spin, and I do this for a living. It's like, I don't know how it functions. So before we used to have a single transmitter and it would broadcast out, and you remember that multi-path thing from before? State of the art before 11N was we'd have diversity antennas separated by about the full width of a signal or a wavelength, so that we could figure out which signal got there first and which was the best quality, and then the receiver kind of bundled that together and built the packet back out. There's a concept called multiple input, multiple output, right? MIMO. And you're going to hear anything around telecom stuff moving forward. Massive MIMO, multi-user massive MIMO is the big deal. But the idea is that now we have more radios, we have more antenna. In parallel, we can blast things off in aggregate, and the other side will pick them apart and build them back together. For the most part, it was the transaction information from a single user, right? The big changes recently, both in 5G and with wireless, is be able to do that for multiple user sessions at a time. So this is just more of the same. Spatial multiplexing is what I was talking about, where we can have more data from more users being passed through at the same time. I threw this in because people always ask me, what's good, what's bad, how do we deal with network? How do I know that my network is good? It's like, well, your network is only as good as the sample of time where you're looking at it, right? It's a dynamic, living, breathing thing, okay? And a lot of that has to do, in my world, has to do with how full is the warehouse, right? If the warehouse is empty, life is good. I look like a hero. When they pack it to the gills and put things in the aisles and do everything else, our wireless stinks. It's like, okay, let's look at what it was when we tested it and where we are now, right? So there's basically three sets of criteria. Milliwatts, it requires you to be able to measure the electromagnetic energy at a particular point. Really hard to do, right? Decibels is usually the way that most professionals will work, okay? And it is a negative scale. It goes from, say, 30 to 90, and I'll give you a better range of this in the next slide. And then RSSI. So if you open your iPhone, you open your Android phone, you go to network thing, and it says, this is the network we're connected to and the type of security, and here's the RSSI. The RSSI is whoever wrote that program used whatever math they wanted to, and they used whatever scale they wanted to. Sometimes it's 0 to 60, sometimes it's 0 to 255. Don't know. It's useless. But people live and die by it because, it's green, or it's yellow, or it's red. What do you want me to do about it, right? So this might be the picture you want to take. So in terms of dB, right, 30 to 40 is perfect world. You're in an isolated room. There's no interference. You're right next to the network. Negative 67 is kind of where we see the cutoff. So if I see anybody's in the kind of 40 to 70 range, we're okay, right? Anything beyond that, we're not okay. And that's the cut. All right. A couple of things that happened in 11N. First, it was the first release for multiple input, multiple output, multiple radios. They came up with the idea of taking channels and banding them together in the 5 gigahertz range. So instead of having 20 megahertz wide channels, we can put more data on. So I'm going to take more time, and I'm going to use more bandwidth, but I can get more done quickly, right? So they had 20 and 40 megahertz channels that help move things along in the 5 gigahertz range, okay? One of the things that caught people off guard with when more radios came is the power over Ethernet standard needed to be adopted or enhanced to put more power on the line so that you could run more radios. You just had more stuff pulling electrical draw. As we get up to AC, which I think this gentleman was the only one that had it running, up to 8 streams or 8 radios, 2 antennas per. It ran, you'll see, up to 160 megahertz. So they took a whole bunch of channels and combined them together. So supposedly you could get 866 megabits per second. That's all true, and all the advertisement is true, right? The hassle is the further you get away from a 5 gigahertz radio, the more the signal depletes and the harder it is to do any of this. So you can think, even in the perfect conditions, if I'm working with an access point and I test something at, say, 2 feet, and then 4 feet, and then 8 feet, and then 16 feet, I'm expecting that with each of those linear steps back, we're going to drop our coverage by some amount that is proportionally going to get worse the further I get away from it, right? And channel bonding is the concept that I've kind of been alluding to, where with channel bonding, I can either have a bunch of small packets or, all the way down to a single massive packet. It's remarkably effective at pushing a lot of data through a network quickly. Just remember, like, if we're doing that, I get all of the bandwidth and none of you get anything. So deploying this has to be used judiciously, so that, because not everybody's guaranteed access to the network, right? I can stranglehold the network doing this. I did this talk 10 years ago at a Progress event, okay? It wasn't this talk, I'm sorry. I did the concept of wireless when Wi-Fi 6 was the next thing coming, okay? And it's been out for a couple of years now, right? So it took 8 years for what was on the drawing board to actually show up in product, right? Most products that you buy now have a Wi-Fi 6. If you bought any sort of modern phone, it's got Wi-Fi 6, and your laptop, you'd be hard-pressed not to have Wi-Fi 6, right? Up to 7 gigabits. Tri-band, so now they're using 6 gigahertz bands, okay? It's got wire-like latencies, wired network type latencies, right? Lots of headroom for improvement. It's the next big thing, yada, yada, yada. Most of it's true. Most of it, what we talked about, was actually true. This is the big one, right? So we've got Wi-Fi 7 started. It's 2, 5, and 6 gigahertz, 4,096 QAM. What's that mean? If you think that one wave is 1 bit for one user, okay? And I can deform that wave in such a way that I can, instead of making it a perfect sinusoidal wave, I can add a second piece to it and deform it, right? So remember, if it happens accidentally, it's interference. If we do it, it's, modern engineering. 4,096, what we can do is we can take 4,096 requests for a single wave and mangle that wave in such a way that when it comes out the other side, we break it down into 4,096 pieces. Mind-boggling. For anybody, yeah?
Is the interference then not even worse because you're losing more information?
So, sort of. So on the access point side, there's all kinds of error correction. It's not error correction, but that's the way I think of it, because they're deforming the waves, right? So just think about that. One wave, it's 2 inches. That you can break it down to that level, and the next wave of the next spec is going to double that. It's mind-boggling, right? Multi-link operations where we link frequency. So up until Wi-Fi 7, you either worked at 2.4, 5, or 6 gigahertz. Now what they're able to do is do channel bonding across multiple frequencies, okay? And multiple resource units. It basically means that we're going to multiplex a channel for multiple users. So it's not just one user anymore. Now the wait for people standing around trying to get access to the network significantly decreases. Now everybody's sharing the one resource. So if there's 2 or 3 people in a room, you're going to get onto the network quicker. It's going to take you some more cycles to get your complete message put through, but you're not going to be waiting around. There's an interesting phenomenon when you turn that on in a sports stadium, train station, the conference, out here when everybody comes out, all of this stuff is really around high density mobile user bases. Okay. All right. 2.4 versus 5 versus 6, right? If everything's being equal, the same amount of energy can come out of an antenna. 2.4 gigahertz is going to reach twice as far as 5 gigahertz, right? And same proportion for 6 gigahertz. Right? So the practical implication for that is if I'm wiring a place for 5 gigahertz coverage, I need twice as many access points. Doing this kind of presentation at a way higher level to the C-suite saying you need twice as many access points can be a tough sell at times. Just to put it in perspective, the sizes of the waves, right? The 6 gigahertz wave at 1.9 or what's that? 0.05 meters. They're tiny, right? They're tiny. So just imagine that if it's that small and I can produce billions of them in a second, how that propagates, right? Just a comparison between the three. As you go across the 20 megahertz channels, or 20 megahertz channels, we got 11. That's really 3, right? But as we get into the 6 gigahertz range, we got 59 channels, right? We have lots of spectrum. We have lots of speed. Coverage is the interesting thing, right? All right, let's get into the cell phone. Any questions on the Wi-Fi component of this yet? No. All right. So we're going to kind of hopefully bring the move in the Wi-Fi to the move in cellular technology. And guess what we're going to talk about? We're going to talk about frequencies. We're going to talk about beam forming. We're going to talk about interference. We're going to talk about regulated speeds. Right? But here's the general move in cell history. Right? In the 80s, we had analog to voice, then digital voice, and around the 2000, we started having mobile broadband. Right? That's where things really started to take off. That's the 3G networks in the 2010s, and in kind of 2020, we've got this proliferation of devices. So it's a chicken and egg sort of thing. We have all these devices that have all these capabilities that all draw on the network. The network folks have to fight to stay ahead, and so it's this slinky effect of who's going to get there first. And the worst thing that can happen is you have a device that's capable, and you have a public network that's not capable of keeping up, right? And then things crash, and oh, this stinks, and so there's a huge amount of pressure. So 5G works on 3 chunks of spectrum, right? There's less than a gigahertz, okay? So remember, in Wi-Fi, we were talking the bottom was 2.4 gigahertz, right? We're talking about hundreds, some 600-700 megahertz, 900 megahertz, really big waves that go really, really far, right? Because they'll penetrate lots of product. So huge amount of coverage because they're slow, not a lot of capacity, and the latency is pretty substantial. Okay. It's put in low to kind of build low, good, better, best sort of thing going up the thing. Latency on a network that runs in 900 megahertz network is pretty substantial. Between 1 and 6, that's all of our Wi-Fi frequencies, right? 2.4, 5, and 6. And you'll see it's moderate for coverage, for latency, for capacity. When you get above 24 gigahertz, which is really the killer piece for the 5G coverage, right? The millimeter waves is what they're called. An enormous amount of capacity. Why? Because I have 24 billion waves going at a time on a really high energy thing. So they go really short distances before they get attenuated, right? But if I can capture the sweet spot for that, I can move massive amounts of data, right? So what makes up a 5G network then? You have a central server someplace, and really the trick for 5G being rolled out, you'll always hear people talking about, oh, we're rolling out our 5G, we're moving it to this capacity or 5G plus or whatever. What they're doing is they're building out little sub-networks all over the place to be able to be allowed to bring that millimeter wave network, right, to you. And it's a proximate thing, meaning you need to be close to be able to listen to and hear a network, okay? So one of the concepts they use are small cell or picocell networks. All it means is that right across the street there's a park, right? Park's full of trees, and people drinking beer. Went over there the other night, right? If we were going to build that out in a network, those trees in a millimeter network, even if I put the best signal antenna on the side of this building, trying to get them through the trees, never going to work. So what would happen is we'd put some sort of point-to-point from the building into the center and put a bunch of antenna around that park, and everybody would enjoy the kind of the freedom of 5G coverage. It's that discrete, right? So when you see the big maps, and in the US it was common, you know, oh, Verizon's got the biggest coverage of 5G. It's like, no, you don't, right? Like, it was on this street corner, and it's that street corner, and then the connecting road and the 50 miles to get to the next town, it's all the old 4G coverage. They say, well, if it's 4G, we're going to build it out. It's like, all right, well, then say that. So the big 5G things, right, is one, the network. Massive MIMO is really the kicker. When you add all the capability of the network, that I can do more for more people all concurrently, that's the big win. It uses beamforming as a technique, and one of the things that has come from the Wi-Fi world into the cellular world is they have these antenna arrays that are intelligent, okay? So as time passes and you have trees grow or trees hit and the leaves fall down, or it's wet or it's raining, or all the things that cause interference or signal attenuation, what they can do is the antenna array is intelligent in the sense that it can use beamforming to get a more perfect signal to whoever the recipient is. So this communication between the two antennas that say, that was good, this is better, less good, go back to where you are, and that happens in real time, right? There are a handful of wireless vendors that do the same sort of thing. So they have actively controlled gain to their products, right? So, and that it's full duplex is a big deal. So the convergence is a real thing, right? So cell phone carriers, public network carriers have an issue in really high density environments of what to do with all this traffic, right? It used to be that you'd come to one of these events and the keynote speaker, you know, who's got a phone, who's using a phone, and who's got two phones, and oh, who's got three, and you know, people would stand up, and the more phones you had, I guess the higher you were in the pecking order of coolness, right? Everybody's got stuff now, right? Everybody. And the push is to put more and more devices onto that, the whole Internet of Things, you know, sort of deal. You know, with cars and you know, your refrigerator will tell you you're out of milk, and your laundry detergent or laundry machine will tell you you're out of detergent, and all those sorts of things. It's all capacity, right? So this concept of backhaul. Just think about a big building in an urban center. You know, pick a skyscraper in New York City, right? Everybody that's in there has a phone. Everybody in there has an iPad or a computer or whatever, right? You're hard pressed to find any mobile device anymore that has a physical network card in it, right? So the idea is it's all wireless. It's all wireless. It's going wireless. It's not going back. So what did they do? Is the phone companies want to get all of that voice traffic off of their voice network. So buildings will install equipment that will take and move that traffic, and it will look like your phone carrier. It actually happens through the wired network in the building to be able to backhaul it and get it off of the Wi-Fi. So it frees up the wireless spectrum, and you think you're on their thing. I don't know whether it's true here or not, but that concept of moving back and combining things is a big deal. So one of the things that comes with then is if I'm on my phone and I walk into a building, how do I get you from the cellular network to the wired network? And there's a whole concept called Hotspot 2.0, and it should be invisible to you. But the idea is that you're going to authenticate once onto a network, and that it's kind of single sign-on for voice. Okay, it's a great idea. A lot of implementation issues, but in 10 years when I do this again, I'll get to scratch off the many implementation issues. So, as developers, kind of, what can we do knowing all these sorts of things, right? Especially if you're doing development for inside the four walls sorts of things, you need to know your coverage, right? You need to know your bandwidth. You need to know that your network's good. You need to understand everything around your network, right? Remember when coding for memory and disk was an issue? Well, this is the new currency, right? Design patterns for slow or ultra-connected, ultra-slow connections. Really, if it's important to you, you want to be able to build applications that will work either connected or disconnected. And that paradigm is a really hard one to work with right now. What can you control? If you design things for low or lousy bandwidth, you're going to be happy. If your network requires ultra-fast, super speed, blah, 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 and you don't have it, bad things are going to happen. Right? Security, right? You own it in terms of managing, what people can do, locking down devices, making sure that your applications are contained. Big deal, right? In the network transition we've already talked about. What can't you control? Can't control the infrastructure necessarily. Inside the four walls you can, but if you're relying on outside, you're going to have some trouble. There's interference everywhere. So if you're doing design for an application, and it works in my office, right? Well, if I take it on to Central Park in New York, and now I've got literally millions of devices that are interfering, might have some problems. I can't control where a user's going to take the device. Power consumption and data consumption. Power consumption is actually a big deal in mobile development. Is how do you manage that? The things that cause draw on a mobile device, having the screen on, having the Wi-Fi running, and having the cellular radio running. Right? Those are the big three, in terms of straws drinking out of that margarita, those are the ones. Nothing else matters, right? So, like I said, wireless is the future. Nothing's going back to wired, right? Security concerns are, that's just universal. Interference is beyond your control, right? So we need to work through that. And this whole concept of bridging LAN to a WAN and doing it seamlessly. 5G and the high-end wireless, for my purposes, okay, for the types of things that we do as a company, they're effectively the same thing, right? So have the same kind of capabilities. I could get by. If somebody said, all we have is really good 5G coverage at our facility, can you work on it? Yeah, we can, finally, okay? 5G is not everywhere yet, and it's going to take a long, long time for it to still roll out, right? So there's still some, and on the high-end Wi-Fi thing, nobody's selling products to use it yet, right? So it's a bit of a future statement, but the idea that those are going to converge, I think is very, very likely over time. So, like I said, in 10 years when I do it, here's the convergence sort of deal. That's what we got. Hopefully I didn't make your head spin too hard or hurt too much. Questions, comments? I've just numbed it out of you, huh? Yeah.
About mobile, I think that you can actually choose to use Wi-Fi to call. So it is.
That's what I've been doing all week.
Yeah, but so then you don't have this. Then you only have to manage the Wi-Fi. Then.
But that only works if you're under a perpetual blanket of Wi-Fi coverage. So if I'm walking out in the street, I'm over in the park, and I have Wi-Fi, right? So that you're right, right? So, hey, thanks for spending a little bit of time with me. Thanks for coming out. Thank you for the.